Hello Math 1224, this is Dr. P with Lesson Launch 22. So in this video I want to set up a little bit of background about how the different terms of a Fourier polynomial play with each other. So just as a reminder, here are what the terms of a Fourier polynomial look like. There can be many of them, but there's essentially three types. There's a constant polynomial, which actually you don't have to think of this as a separate type. This is really just a naught times cosine of 0x, because cosine of 0 is just 1. I just want to show how that fits into the rest of this scheme here. There's a sub k, sorry, not a sub k, there's a sub k times cosine of kx, and there's b sub k times sine of kx. So really, if you want to think of it this way, there's really two different types of terms. There are these where k is greater than or equal to 0, and there are these where k is greater than or equal to 1. I guess you could make these also k greater than or equal to 0, but if k were equal to 0 for this term, you'd have a big fat 0 there, and the sign of that would be 0, which means the whole term would cancel out. Anyway, in this video, we're going to look at how these terms play off of each other. In particular, there's a very specific question I want to ask, which is, if we integrate the product of two of these, these terms over a period, what do we get? Now, when I say two of these terms, what I actually mean is we're going to take these terms of the Fourier polynomial and multiply them by various cosine of kx's and sine of kx's and see what happens in the integral. In other words, we're going to multiply one of these terms by just one of these basic building blocks, a cosine of kx or a sine of kx, and see what the integral is over one period. Now again, in this exercise, the period is always going to be considered to be 2 pi. Now that might seem a bit strange because if I look at these different terms here, like if k is 2, for example, this cosine function, cosine of 2x, has periods smaller than 2 pi, but you could still think of it as having a period of 2 pi because it does repeat itself every 2 pi units. It just also happens to repeat itself every pi units. So any of these functions we can think of as having a period of 2 pi. Okay, anyway, enough chit-chat. So what we're going to try and do is we're going to try and integrate two of these things. And I probably won't do all the different possible combinations because, who has time? Who has the time or attention for all of that? But I just want to do a couple of examples just to show what kinds of interesting things can happen. All right, so first of all, let's try integrating from 0 to 2 pi the product of one of the cosines with one of the sines. So I'm going to try integrating the product of ak, cosine of kx, times a sine of something else. Let's call it mx. I was going to use L, but L is so hard to tell from the number 1 that I think I'd rather use m. Okay, now in this example, k and m are both natural numbers. Well, k could be greater than or equal to 0, and m can be anything greater than or equal to 1, and they could be equal. So it's possible that they're equal. All right, and we're going to do this little trig integration exercise. Now, you'll remember from the start of the semester, this is one of those where we might have used integration by parts. So we might have identified one of these pieces as a u and one of them as a dv, and then write down, okay, this integral is uv minus integral of v to u, and then the thing refuses to die because you still have a sine and a cosine, or maybe a sine and a sine, or something like that. In the next integral that you write down. You keep going, and eventually you see, oh, we're back at the same integral that we started with, but times a funny constant. I could do all of that, but that would take about 5 to 10 minutes, and I don't feel like it. So instead, we're going to do something else. We're going to zoom out and look over here. Hey, there's my integral table there. I actually put the whole thing over here, but I think we just need this part here. Let's just use that, why don't we? Okay. So I'm going to just keep that in my window here. I don't know if that's visible, especially in YouTube quality. You might have to take my word for the entry that I'm writing down, but we're going to be using, which one? We're going to be using, I think in this case, this integral right here, number 12. Okay, so by number 12, the integral, let me just, move all the way over here. I'm going to write down what the integral is I'm trying to find, and then move over so I have plenty of room to write the answer, because these are kind of lengthy and unwieldy. Okay, so that's the thing I'm trying to find the antiderivative of. Now let's move on over. Okay, that integral is going to be, now I have to think about my a's and b's and my k's and m's here. I think it might be more advantageous to, well, let me just identify here. We got a constant of ak there. The coefficient in the sine function is m, so a should equal m, and then b should equal k, and we're going to use entry number 12. Remember, when I use the table, I always try to write down which entry number I'm using so that everybody can follow. Okay, anyway, so what do we have here? So this is going to be 1 over b squared minus a squared, so k squared minus m squared, whatever that is. I said that, I just realized that we actually do need to restrict out the case where k is equal to m. So we're going to assume for now that k is not equal to m, and I'll just mention what will happen when k is equal to m. So here I get 1 over k squared minus m squared, because just so you know, that there's that restriction in the table. I can't have a equals b. Anyway, get 1 over k squared minus m squared times b, that's k, sine of mx, sine of kx, I think, plus m times cosine of mx, cosine of kx. All of that plus c, okay? Which looks like a mess. Looks like kind of a nightmare. But now, if I'm trying to integrate this from 0 to 2 pi, here's what's going to happen. This is actually kind of sweet. That means that I can just forget about this constant here, and I can just evaluate this at 0 and at 2 pi. But think about what happens when you do that. When you evaluate this at 0 and at 2 pi, I've just got a bunch of periodic functions here. Whatever the value of this is at 0, which actually you can say exactly what it is, it's just 0. It's going to have the same value at 2 pi, and the same with this. When x is 0, I get m times 1 times 1, and at 2 pi I get m times 1 times 1. So the point is that this entire thing here evaluates to the same thing at 0 as it does at 2 pi. So this entire thing here is equal to 0 when k is not equal to m. Okay, and by the way, when k does equal m, then I'm talking about the integral of a sub k times cosine of kx times sine of kx. I'll just tell you, that's going to, usually the way that we integrate this is we rewrite this as 1/2 sine of 2kx. And then that integrates pretty easily, and that also integrates to 0 over any period of the function. So even when k is equal to m, there's still nothing left when we integrate the product of these. Okay, so anyway, so just to summarize what we've done so far, what we've shown here is that if I take any of these and multiply by any of these, that is any cosine term times any sine term, integrate from 0 to 2 pi, I get 0. Okay, now I'm not telling you anything about why that might be important for us to know. I'm just going to ask you to keep that in your back pocket until class. All right? So now let's talk about what happens if we take two cosine functions. So I'm going to switch colors here, and we're going to talk about the case of two cosine functions. Okay, again, we're going to use the table to do this. So let's see what happens if we take two different ones. I'm trying to figure out how I can get all this in my window here. Actually, I can move up here. That might be better. Okay. So the integral from 0 to 2 pi, actually, let me just leave off the limits of integration right now. The integral of, what was it, a sub k times cosine of kx times some other cosine of mx, where k is not equal to m. Here, this assumption is going to be really important. K is not equal to m. That integral, again, by the integral table, so what do we got here? A equals k, b equals m. And we're going to use entry number 11. We're going to get, what is that? 1 over m squared minus k squared. There you see it's really important that k not be equal to m. Times, let's see. Sorry, I got lost in thought there for a second. Times b. What is b? That's m cosine of kx. Sine of mx minus k times sine of kx cosine of mx. Sorry, reading this table takes a while. And then plus c. We're not going to worry about the plus c because, again, we're integrating from 0 to 2 pi, which means we're going to evaluate this doodad at 0 and 2 pi. And again, you get the same situation here. This whole thing here, when x is 0, it evaluates to the very same thing as it does when x is equal to 2 pi. And in fact, in this case, both terms evaluate to 0 at both of those places. So this integral, again, is one big fat 0. Okay, so just taking stock of what we've learned so far. Okay, if I take one of these cosine terms and multiply by one of these sine terms, any of the sine terms, the integral comes out to be 0 over any period. If I take two different cosine terms, I will get 0. That is the product of, the integral of the product of any two of these cosine terms over a period integrates to 0. I could say the same thing. I won't bother showing it because I know you're probably bored to tears with all this table work. But if I take any two different sine terms, I will also get a 0 if I integrate over one period. So that leaves one thing. What if we take the same cosine term? That is a cosine of kx times a cosine of kx. Integrate that. Well, let's find out. So I'm going to do this in a different color still. So what happens if I integrate the function a sub k times, cosine of kx, and then multiply that by cosine of kx over one period? Okay, well, first I'm going to work out what the integral of this is, the antiderivative. That's a sub k cosine squared of kx dx. And now I'm going to use my super famous trick that I do with cosine squared functions, which is I turn them into something a little bit more hospitable. I'm going to turn this into 1 plus cosine of 2kx over 2 dx. So then the antiderivative is going to come out to ak times, what is that? That's 1/2 x plus, and then what do I get there? I get sine of, I think I get sine of 2kx over 2 times 2k, because now really if I wanted to make a big deal out of this, I would do a substitution here, but I'm just going to count on you to look at this and see what happens if we take the derivative of this. Well, by the chain rule, we end up multiplying by a factor of 2k. That's what gets rid of that in the end. So anyway, that's my antiderivative. So the integral from 0 to 2 pi of ak times cosine of kx times cosine of kx dx, that's going to come out to this thing, a sub k times this deal here, 1/2 x plus this sine of 2kx over 4k, evaluated at 0 and 2 pi, and then subtracted. Now, would you look at this? This thing here, whether x is 0 or 2 pi, evaluates to 0 each time. Evaluates to 0, evaluates to 0. But this thing, this one is fun. This gives me a sub k times 1/2 of 2 pi minus 1/2 of 0. And that evaluates to a sub k times pi. Okay, now again, I'm not going to say much about why that's important for finding Fourier polynomials. I'm just going to ask you to keep that result in your back pocket. So just to summarize, here's what we discovered in this video by doing a bunch of little grunt work here. Okay, so any of these terms will interfere with any of these terms in such a way as essentially to cancel everything out over a period. Any two different ones of these terms or any two different terms from here also will interfere with each other in a way that cancels each other out. But if I take the same term either from here or from here, I didn't show these, but the same logic applies. If I take the same term from here or from here, then I get that coefficient times pi. And we're going to use that result in class to discover what the best possible coefficients for a Fourier polynomial would be. Now, just one more thing. Before you go to class, I have one more assignment for you. I'm going to send you a link to an interactive demo on Desmos. I'll just write that down here. Desmos. Desmos. My spelling seems to be suffering right now. Desmos, I think it's called square wave Fourier polynomial, or possibly vice versa. It could be Fourier polynomial square wave. What I'm going to ask you to do is play around with that, and without knowing too much about how to find the coefficients, just figure out what do you think would be the best coefficients for the Fourier polynomial I've given you. I think I gave you one through degree about 5, which might have been overkill. But here's my advice. So you're trying to approximate the square wave in that picture, which is not only fails to be differentiable, but it fails to be continuous in some places. But I still claim you can get a pretty good approximation using a suitable Fourier polynomial. So my advice is play around with some of the coefficients. You will they all start at 0 in that demo, but you're not gonna want to change all of them. You're actually gonna want quite a few of them to be 0. So you're gonna change a select few of them and try and get a Fourier polynomial. It's going to be some big wavy thing that gets as close to that square wave as possible. It's just a little toy I want you to play with before we come to class so that you have some feel for what it is we're trying to do. All right, anyway, see you in class.